Hello, welcome to this module. This module is in continuation to our last module. In the last module I have discussed the electrical and mechanical properties of tissue, how can we fabricate a flexible sensor with PEDOT-PSS as a strain gauge and then insulating material and gold electrode over which there were SU8 pillars. In this particular module I want to emphasize and stress more on the chip for ETM properties. E stands for electrical, T stands for thermal, M stands for mechanical properties. Before we dive into this particular fabrication process, you should have very clear idea about the breast anatomy and also the breast cancer stages. Alright. So, I have got you two quick videos to look at and then we continue the class. So, if you see the slide, the breast generally or not generally, the breast anatomy is such that it consists of ducts, right, it consists of lobes, you see lobes, duct, right, and then there is a pectoral muscles and then there is fat. Alright. So, duct, lobe, fat and pectoral muscles. Now, if the cancer occurs in duct is called ductal cancer, it occurs in lobe, lobular cancer, right, it is both duct and lobe, then mixed tumor cancer. If there is an inflammation, inflammatory cancer, if there is a mucus, mucigenous cancer. So, several kinds of cancer are there and the very important is triple negative breast cancer where all the markers are absent. So, this particular chip would probably help the oncopathologist to come up with a better diagnosis, because we are adding 3 extra modalities or 3 additional modalities to the existing modality, which is biomarker. So, if you see the video, I am playing the first breast anatomy video.
Breast cancer is the most common form of cancer in women today. Knowing more about your own breast anatomy can help you in early cancer detection and prevention. Your breasts are connected to small masses of tissue called lymph nodes by way of lymph vessels. The lymph nodes are responsible for collecting bacteria, cancer cells, and other unhealthy material. You have groups of these lymph nodes under your arms, above your collarbones, and behind your breastbone, as well as in other parts of your body. Each breast is made up of lobes, lobules, and ducts. The lobes consist of smaller lobules that contain groups of tiny milk-producing glands. When a breast is producing milk, it passes through the ducts into the nipple, where it exits the body. Breast cancer most commonly develops in the lobules, glands, and ducts of the breast.
Okay. So, in this you have seen in detail what I was talking on the slide about the anatomy of the breast. Now, let us see how the breast cancers different stages are there, and let me play it.
The staging of breast cancer refers to the extent of the disease. The cancer stage is based on several factors, including the size of the tumor, if any lymph nodes are involved, if the cancer is invasive or non-invasive, and if the cancer has spread to areas beyond the breast. Stage 0 is considered a non-invasive breast cancer. In this stage, there is no evidence that the cancer cells have spread into neighboring breast tissue beyond the duct or lobule. Stage 1 is considered an early stage of invasive breast cancer. When measured, the tumor is no more than 2 centimeters in diameter, and there is no evidence that the cancer cells have spread beyond the breast. Stage 2 is divided into subcategories of 2A and 2B. Stage 2A is invasive breast cancer, where the tumor is either a maximum of 2 centimeters in diameter and has spread to the lymph nodes under the arm, or the tumor is between 2 and 5 centimeters in diameter but has not spread to any lymph nodes. Stage 2B is a little different in that the tumor is either between 2 and 5 centimeters and has spread to underarm lymph nodes, or the tumor is larger than 5 centimeters but has not spread to the underarm lymph nodes. Stage 3 is considered a locally advanced cancer, and it is also divided into subcategories of 3A, 3B, and 3C. There are two main scenarios that can occur with stage 3A breast cancer. One, where the tumor is no larger than 5 centimeters in diameter, but it has spread to underarm lymph nodes that are growing into each other, forming clumps. The cancer may also have spread to the lymph nodes near the breastbone. The second scenario for stage 3A is very similar, with the exception that the tumor is larger than 5 centimeters in diameter and that the underarm lymph nodes are not adhered to one another or other tissues. Unlike the other stages, in stage 3B, the tumor may be any size and has spread into the skin of the breast or chest wall. This stage may also include lumps in the skin of the breast or swelling of the breast. In stage 3C, the tumor may also be of any size, but it has also spread to lymph node areas above or below the clavicle, the chest wall, and/or the skin of the breast. Stage 4 is considered distant metastatic cancer, meaning the cancer has spread to other organs and parts of the body.
So, what you saw? You saw that there are several stages of breast cancer, stage 0, 1, 2, 3, 4. Earlier you diagnose any disease, you can have cure for the disease, right. So, early diagnosis, early screening is an important parameter in this field, right. Earlier you screen, better, earlier diagnose, better. Unfortunately, because of the lack of awareness, generally when the women knows that there is some problem and they go to the hospital, it is already stage 3 or stage 2, all right. The reason is, like I said, lack of awareness. It is very important that we start awareness, because we are working on this research problem, that a woman has to go for mammography, which is a screening test for breast cancer. Age wise there is a requirement, if it is less than 40 once in a year, above 40 twice in a year, or vice versa, you can just quickly see it. But the point is, it is very important to go for mammography, all right. So, let us see the statistics, and then you will understand why I am saying it is extremely important to screen and regularly test. Once in a year is not a big deal, all right, and lot of government facilities gives give this facility for free, all right, or very nominal price of like 80 rupees or 100 rupees. So, if it can save a life, it is worth spending thousands, but at the same time lot of people cannot afford. So, how about 100, right. So, if you see the government initiatives, there are very good initiatives for health care in particular, and if we are aware, we can take help of those initiatives, including I recently came to know that particularly in Karnataka state there is a government initiative where the government will give about 1.2 lakh or 1.3 lakh, something around that value for heart operation. It is really important and good initiative, all right. So, but the point is we should be aware, right. If we are aware, we can use initiatives. Okay. So, this I am talking a little bit slightly deviating the topic of sensor actuators, because you have to learn sensor actuators when you have a disease, but why to have disease, right, why to not stop this thing. So, if you cannot stop, at least why do not you screen it at early stage, right. So, that is our reason of why I was talking about. So, if you see the slide, you will understand that we are talking about phenotyping of breast cancer, not genotyping of breast cancer, and according to Globocoin, in September 2018 the cancer burden has risen to 18.1 million cases and close to 9.6 million cancer deaths. Is a huge value, and you can see here that the incidence versus mortality, the lung cancer leads to quite an extent. You can see here incidence of lung cancer right, 11.6% of all new cases, about 2.094 million cases, where if you talk about breast cancer, again close to 2.089 million cases, colorectal colorectal, I am sorry, the cancer, which is about 10.2% or 1.8 million cases, followed by prostate cancer about 1.3 million cases, and stomach cancer about 1 million cases. When you look at the mortality ratio, you will see that lung cancer 18.4% mortality, that means 1.8 million deaths. When you talk about colorectal, you can see about 8,81,000 patients die. Stomach cancer about 7,83,000, liver 7,82,000, while breast 6,27,000, and this is for both sexes and all cancer for all ages worldwide. But if you see, the overall burden is huge, all right. So, what we can see is that breast cancer is a leading site of cancer in women accounting for 27% of the cases, and that is why a very important problem to address and to find a solution. Now, the high rate of incidence, relatively lower rate of mortality for a breast cancer suggests that accurate and early diagnosis can go a long way in saving life. You can see in terms of incident it is a number 2, but in terms of mortality it is a number 5. So, if we can get a better diagnosis, better screening, better sensors, right, then we can still reduce this mortality factor. Okay. So, as you have seen in the video, what we see is that the stages, when you say stage 0, the tumor size is very small and inside the glands, right. In lymph nodes there is nothing, spreading is not spread, and survival rate is about 100% for 5 year survival rate. For 2 centimeter stage 1, again lymph nodes there is nothing, and confined to the breast area, not outside, which is a good point, and 100% is a 5 year survival ratio. So, this too is where we should identify a patient, all right. However, as you progress further, where it is stage 2 and the tumor size is about 2 to 5 centimeter, and now the lymph nodes are affected, you can see here the representative image, the lymph nodes are affected, and then further this is confined to the breast, not outside. So, still it can be cured, and you can see that survival rate is 87%, but as you go to stage 3 and 4, the difficulty or complexity increases. Stage 3 is 5 centimeter and larger, stage 4 any size, stage 3 affected by cancer. Cancer has reached to the muscles and skin, and you can see here, you can see the lymph nodes, right, while in this case it can be anywhere, including the tumor in brain, confined to the breast area, not outside, but here it can be of any part of the body, and this is about 20% only, this is also 61% only. What I prefer is, how about we try to make a system that can have these things, at least we can cover stage 2. All right. So, based on tumor size stage 0 to 4, based on the sites, then you can say that it is a lobular carcinoma in situ, ductal carcinoma in situ, invasive lobular carcinoma, and invasive ductal carcinoma. Based on the receptor status, you can divide into 4 states: HER2 plus minus, luminal A, luminal B, triple negative HER minus, HER2 minus, and HER2 enriched HR minus and HER2 plus. So, these are based on the receptor status. If I see the background or workflow of diagnosis and staging of breast cancer, then you can see here that once it is diagnosed, there can be many ways of diagnosing the cancer. One is physical exam or history, second is clinical breast exam, which is called CBE, third is mammography, MRI, ultrasound, fourth one is genotyping, which is blood chemistry studies. We are talking about phenotyping, so we continue with a biopsy. If the biopsy is done, then the cells are taken to study, which is called cytology. So, cytology, then core biopsy, incisional biopsy, and excisional biopsy. If further divide it, then there is a histopathological analysis where all the biomarkers that I was talking about, ER, estrogen, PR, prostrogen, HER2 plus are studied, and then based on that the staging and subtyping is there. So, this is the process or workflow for diagnosing or staging of breast cancer. So, 73% of all breast cancer is HER plus 2 HER minus HER2 minus, where 13% which is also called triple negative breast cancer, very dangerous, HR minus and HER2 minus, while 10% and 5% are for HR plus 2 HER2 plus and HR minus HER2 plus. So now the point is we require an alternative modality and we need to study physical properties of tissue. So how about we study physical properties of tissue as an alternative modality. So that is why we were somewhere in this particular domain, biopsy domain, alright. So now why which physical properties of tissues we have to study? We can study the electrical properties, which is resistive and impedance measurements. We can study the conductivity and diffusivity, which is thermoconductivity. We can also study the mechanical properties like elasticity and stiffness. If we couple all these parameters along with biomarkers, can we bring the false positive and false negative signals down, and can we also have a novel or alternative or additional modalities to reduce the or to not only reduce the false positive and false negative, but also to diagnose triple negative breast cancer. So that is a bigger picture of this particular research. If you again see the screen, you will find that this is how the MRI is done, right. Most of you have seen there is separate lecture is required for making you understand how MRI operates. For now you just understand that MRI and mammography both are used for screening the patient. If there is a suspicion region, then the patient is asked for biopsy. Breast biopsy is done with the help of needle and the tissue is taken out like you can see here, and tissue is sliced further. When you slice tissue further with microtome, then you can get different biomarkers. Here you can see H&E staining, P63 brown SMA red, estrogen and prostrogen, which is PR, ER, P63 SMA and H&E. Okay. Now what we are planning is, can we measure the electrical, mechanical and thermal properties of this tissue, and for that what we can do. So now you take this particular example, okay. This is very important, and then we will see that how can we fabricate this particular tissue, right, this particular chip, and place it for fabricating for understanding the tissue property. So if you see this chip, let me see the next slide. Yes, now this is a chip that we have to fabricate, alright. What is this chip consist of? This chip consists of a heater, which you can see here, right, and then on that heater there is an insulating material. Now you all know how can you fabricate heater, it is very easy, right. You deposit a metal, then spin coat photoresist, soft bake, expose it with mask, develop the photoresist, then hard bake, then etch the metal, then strip off the photoresist with acetone, and you have a heater. After heater you have a insulating material. On insulating material you can have interdigitated electrodes. Once you have interdigitated electrodes, again you know it, how can you fabricate? You deposit metal and use lithography technique to form interdigitated electrodes. On these interdigitated electrodes you can deposit the sensing material, and this sensing material is your piezoresistive material. Now if you have a piezoresistive material, that means that I will just use a block diagram to make it easier. So there is a heater at the bottom, which is I will call H. On that there is a, let us say interdigital electrodes, which I call IDEs, on which you have the sensing material. So I will say piezoresistor, so PZ, alright. Now if I apply force, then the resistor, piezoresistor, which are this particular 4 blocks, this should show me the change in the resistance, but it will only show the change in resistance when my silicon will bend, but silicon is hard. So what can I do? That is why I can now create a diaphragm, and this is what a diaphragm you can see here. The diaphragm is created so that when I apply a force, then this diaphragm will bend, and when it bends there is a strain in the piezoresistor, and thus there is a change in the resistance. So this is the point. Now if I on the piezoresistor again, so let me again show it to you what exactly this block is, so that you understand very clearly. I am just showing a block diagram, it becomes easier, okay, that way. So silicon, and of course you have oxidized silicon wafer, so we will have SiO2, right, SiO2. On that you have your heater, so I will write H for heater. On that you have again silicon insulate dioxide. Then on that you have interdigitated electrodes, is IDEs. On IDEs you have piezoresistor, so you have PEZ. On that you have on piezoresistor you have again have a insulating material which is SiO2, on that you have gold pad which is AAU, on gold pad you have a SU8 pillars. So, SU8 pillars I will just draw like this, just representative SU8, right. So, this is the structure of this chip. What is at the bottom? There is a heater which you can see here, then there is an insulator and then there are interdigital electrodes which you can see in this particular diagram. On interdigitated electrodes there is a piezoresistor which you can see in this diagram, right. On that there is silicon dioxide over which there are gold pads which you can see here, and then over gold pad there are SU8 pillars which also you can see over here, alright. So, this is the chip, and on the back side of this silicon what you have? You have etching which is your diaphragm, right. So, this is the chip. Now, if I place a tissue on this chip, that means I have a tissue and this tissue is placed on this chip like this, alright. And if I place this chip here, alright, in between what is there? There is a tissue like this, okay. This is my chip. Which chip? This one, alright, or you can say this one. Now, if I apply a force through my indenter, this is my indenter, alright, this is my indenter. If I apply a force through indenter, what will happen? If I apply a force on this tissue, this is my biopsy tissue, So, if I apply a force, then my piezoresistor on the chip will show change in resistance, right. My piezoresistor on this chip will show change in resistance depending on how much force it can observes, right, or it is translated through the tissue. There is a F1 force that I apply through indenter and my chip will get F2 force. This F2 will depend on the elasticity of the tissue or the stiffness of the tissue, right. So, if I know the difference of the force, then I can measure the elasticity or the stiffness of tissue, got it. This force change I can measure with the help of piezoresistor. Now, let us see the second property. This remains as it is, alright. Now, you see, if you see the indenter which in this figure if you see the indenter, there is a electrode in the tip of the indenter, you can see electrode at the tip of the indenter. That means, if I apply voltage here which is let us say voltage one potential of the voltage is here, and on the chip there is a gold pad with SU8 pillars, right, gold pad with SU8 pillars. So, if I apply a voltage here as another pad of this potential, then what will happen? If I apply voltage between V1 and V11, then depending on the resistance of the tissue, my current will change, right. If I apply potential difference, that is voltage between two pads V1 and V11, right, it is like two electrodes, okay. So, electrode 1 and electrode 11, electrode 11 is on the chip, electrode 1 is on the indenter, this one, right. So, if I apply voltage between those two electrodes and if there is a tissue in between, then I can see change in current, and that change in current will be because of the resistance of tissue. So, if I know the voltage, if I know the current, I can measure the resistance of the tissue. So, first we are measuring the elasticity, now we are measuring the resistance. Let us see the third one. What our chip has? Our chip has a heater, is not it? Our chip has a heater here, right. So, if I apply a voltage to the heater, it will heat, that means I can heat my chip let us say at 37 degrees centigrade, okay, and tissue is placed on this chip. Now, if you see indenter has thermistor, and this thermistor would be on the top of the tissue here. So, let us say T11 and the chip is at T1. So, because chip has a heater, indenter has a thermistor, I can measure what is the change in the temperature. If I apply 37 degree centigrade, what is the temperature at the tip of the tissue, which is T11, and from that difference I can measure the thermal conductivity of the tissue. So, now I can measure elasticity or mechanical properties, I can measure resistance or electrical properties, I can measure change in temperature or thermal conductivity of the tissue. So, all three properties I can measure with the help of a microfabricated biochip for ETM, for measuring the ETM properties of tissue or phenotyping of the tissue. Now, this is for particular application, and then where is this tissue kept? This tissue is kept in the casing that you can see here, and this casing is with the help of 3D printing material, 3D printer, all right. So, I will show it to you how 3D printer works in one of the lab class 3D printer, all right. So, if you see here, there is a top panel, there is a PCB, there is a middle part, here is our biochip, this biochip is this one, all right. Then there is a spring and there is a bottom part. When you put everything together, you have a cone in which you can place the tissue, all right. So, this is how it works. So, let me go to the next slide. Here you can see a process flow quickly. There is a silicon, then you have a oxidized silicon, then you have a micro heater, on that you have a silicon dioxide again, on which you have a interdigitated electrodes. After interdigitated electrodes you have a piezoresistor, after piezoresistor you have insulator, and over which you have a gold pads. On gold pads you have a SU8 pillar, and then you perform the lift off technique to coat SU8 pillars with gold. Once you do that, on the back side you can create a diaphragm, all right. So, I will write down here silicon, silicon dioxide, nichrome heater on silicon dioxide, then silicon dioxide on nichrome, right, on silicon dioxide on silicon, this you understand, this thing you understand, okay. I am not writing every time. Then you have interdigitated electrodes on silicon dioxide on your heater. Here you have piezoresistive material on your interdigitated electrodes, which is sitting on silicon dioxide, which is on nichrome, and which is on silicon dioxide further. Then you have gold pad. So, then you have insulator. So, you have insulator. So, SiO2 on piezoresistor on IDEs. I will stop writing down this particular things. Now, you have gold on SiO2 on piezoresistor on IDEs. Here you have this one, you have SU8 on gold pads, and then I am not writing this thing. Then you have SU8 which is conducting on gold pad, and finally you have diaphragm, right, by etching the backside of the silicon wafer. So, this is the process flow for creating a chip that can measure the electrical, thermal and mechanical properties of a tissue. We will show it to you in one of the lab class, paraffinized and deparaffinized, how to deparaffinize the tissue. When you get the tissue, generally it is covered with wax, and this is called patient tissue box or block, and then this tissue is taken out. You can see the paraffin, you have to remove the paraffin, and then this is your deparaffinized tissue. You can see here the paraffinized tissue versus the deparaffinized tissue, all right. Now, this tissue you have to place in this particular conical or cone shape holder, and if you see here the chip or a microchip or biochip here, right, is placed inside this particular 3D printed case holder, all right. So, I'll move to the next section, and you already know this, how to fabricate micro heaters, right. I'll go to next section. These are the interdigital electrodes, SEM images of it, and these are on the there is a micro heater over which, so there is a micro heater, right, on which there is an insulator, on which there are interdigital electrodes, and then if I go to the next slide, you can see here the piezoresistive materials on interdigital electrodes. Here you can see a gold pads on the so on the piezoresistor there is silicon dioxide, on which there is a gold pad, on which SU8 pillars are there, and you can here see the chip against 1 cent. The reason of using cent is that the size of the coin does not change, that is why the photograph is with 1 cent. And here you can see the results. You can very clearly see that the tissue that lies in the cancerous region would be having a different properties, mechanical properties compared to normal tissues. And same way, if you see this particular graph, you can see very clearly that the resistivity of the cancerous tissues is different than the resistivity of the normal tissues. And from this graph, even it is very close, when you understand thermal conductivity, you will understand that the cancerous tissues shows a different kind of thermal conductivity compared to the normal tissues. So, now this is only for 6 subjects, as you can see here, 3 normal and 3 cancer. If I increase it to 6 subjects to 200 subjects, then I will have a more better, or we can have better understanding about how to correlate these 3 properties with the existing modality, that is your biomarkers, right. So, if you have any question, please feel free to ask me in the forum, so that we can discuss further. And to go ahead with this, now I will show it to you this particular tool. So, what we mean is, you can see the video, and in this video what you can see is that there are indenters, right, and these indenters they press against the tissue, and when the indenters press against the tissue, there is a third indenter also. So, once the tissue is there, you press it and then you rotate the tissue, again you press it and you press it from the top. So, you are covering most of the surface of the tissue, which is a better properties, or it is important to understand or cover more area of tissue, because tissue is anisotropic. And now let us see another chip that we can fabricate, which has a different kind of design, but it has interdigital electrodes and heater for understanding the same tissue properties, which is your electrical and thermal properties. Okay. So, what we will do is we will cover that section in a next module. It is a small section. So, you understand that not only the way I have taught you in this section how the chip can be fabricated, but there is another way of fabricating the chip as well. And let us discuss this thing in the next module, so that not to increase this module to more than it is required in terms of length, right. Too much things continuously will bore a person. So, I will see you in the next class with a new chip that can also perform the electrical and thermal properties, or you can measure the electrical and thermal properties of the tissue, right. Till then, you take care. I will see you in the next class.